Welcome to this short presentation on our poster for SYCLcon 2022 named SYCL Concurrency on GPU Platform Empirical Measurement. My name is Thomas Plancourt. I work at Argonne National Lab, and this work has been done in collaboration with Abhishek, Ajay, and Axel. The goal of this poster is to check if a command we can be scheduled in parallel with multiple commands we can be scheduled in parallel, will run faster than the same commands serialized. So what we mean by a command, the SYCL specification says that a command can be either a kernel function or an asynchronous copy. So this is exactly what we will do. We'll try to run a kernel and asynchronous copy and see if they run faster in parallel than in a serial mode. I just want to say that overlapping of this kind of things, this kind of concurrent execution, are an optimization and not required by the specification. So the question is like, which command can run concurrently? Or maybe more precisely, which command we hope can be run concurrently? And one obvious one is we hope that if we run low occupancy kernel, so kernel who are not using fully the GPU, in our case it will be kernel who run on one work item, we hope that multiple instances of those kernel can run in parallel. So we submit multiple kernel parallel for which each one run only on one work item, and we expect them to run in parallel. What you can do, because all of the GPU except one present is here, use PCIe, and PCIe is a fully duplex protocol. You can submit a host to device data transfer and a device to host data transfer, and you expect both of them to be able to run concurrently. So we'll do exactly this. We'll allocate a buffer in host memory, either using malloc memory, this is what will be named by a M, or host SYCL malloc host memory, pin memory, called with a H, and we try to copy this buffer to a device memory allocated with SYCL device. And also you can mix the two, you can take a kernel and a data transfer, and you expect that the kernel and the data transfer can run concurrently. This kind of optimization is really the hello world of optimization, to be able to overlap data transfer and computation. And this poster is exactly that, trying these three different cases and reporting you the result. We'll try on multiple hardware and multiple backend and multiple compiler. Now the question is how to achieve that, how to write your code if you want to achieve concurrency. In SYCL we have two main ways. One is maybe the OpenCL way, where you can create an out-of-order queue, and after submit your command in this out-of-order queue, and then wait, and you hope that the command will be executed concurrently if possible. Then you can do maybe more the CUDA way, where the CUDA way you use multiple in-order queue, and after you submit command in a round robin in this multiple command queue, and then you wait on all this command queue. And this is similar to what we do, for example, with CUDA stream. Maybe a little note before seeing the result on the methodology. So we run each experiment multiple times, and we take the minimum, so we have kind of the best case scenario. What we do is first we run all the commands serially in a mode with serial, and then we time each individual command, and we compute the maximum theoretical command speed up that you can achieve. So it's the mean time, the max time of divided by the total time, and this gives you the theoretical speed up. We do some tuning to be able to minimize all possible overhead from the runtime and everything. So we tune the parameter of each command, so each command take more or less the same time. We do data transfer as big as possible, so the data transfer take large amount of time, so to neglect any overhead possible. And then when we have this theoretical speedup, we run in a mode which should allow concurrency, and we compute the speedup, the serially versus this one, and we compare the two theoretical speedup and achieve speedup. And for example, here we try, I think it was on this iris node, out of order queue. So we'll use this out of order mode. We use where each command will have this, when we have only one out of order queue, and we try a compute kernel and a transfer device to host. We tune the parameter at the end. Each time takes this amount of time, so more or less the same. So the speedup is 2x. Theoretical speedup is 2x. Then we run in a mode with parallel, so in one out of order queue, and we shove 171x. And because it is close to a certain tolerance, we say success. It is a speedup. So now let's see for the result. So we put a table. So in green, that means we achieve concurrent execution. In orange, we have concurrent execution, but if you enable profiling, it will not work. And in red, it is a serial execution. We didn't see any concurrency. We'll show result on multiple hardware. This one is on the Intel hardware, or Iris one. It's a null platform. And we'll use DPC++ compiler with the OpenCL backend and the level 0 backend. In the first column, you will see the in order, where each command has its own in order, and after we submit each command in this in order queue, and the out of order result. So this one is OpenCL. If you see, if you submit two compute command with a really low occupancy, so one work item, you see that we have concurrent execution. So this is nice. If you try to use compute and a memory data transfer, so M mean malloc, not pin memory, we don't see any concurrency. If you try to see concurrency of a compute and a host to device, pin memory, in this case, everything is fine. But we don't see data transfer between host to device and device to host. And that makes sense because this Iris is an integrated GPU, so we don't have any PCI transfer, so this is expected. If we measure with level 0, in level 0 we don't have any concurrency. Please note that those results are a snapshot in time. It evolves pretty quickly. So all the results I say here, it's really not what you can see if you just reproduce the result even today, for example. In the lasted level 0 release or runtime, you can see concurrency now. Now let's go for NVIDIA. So we use the A100 and we compare Intel LLVM CUDA backend to the SYCL with the CUDA backend. So the results are pretty obvious. If you use in-order queue, you have concurrency everywhere. If you use out-of-order queue, you don't have any concurrency. You see here a little limitation that even in in-order queue, if you use malloc memory and not pin memory for your data transfer, you don't see any problem. You don't see any concurrency. It is serial. This one seems to be a limitation of the hardware. If you use SYCL, in SYCL everything is fine. You have concurrency everywhere. This is due to the fact that in DPC++, in Intel LLVM, right now, out-of-order queues, SYCL out-of-order queues are mapped to one CUDA stream. So, of course, you will be serialized. What in SYCL, you map one out-of-order queue to multiple CUDA stream, so you can have concurrency. Some work is done right now in Intel LLVM to be able to support this pool of concurrency. It is the same result on AMD. On AMD, the picture is really similar, with the only difference is that if you use profiling, if when you create your queue, you use in-order profiling, you use profiling, sorry, you will see serialization. So to summarize, we develop a little tool who can measure by really empirically, so no need for event, no need for profiling, because profiling can have side effects, to measure if you have concurrency or not. So please, we are encouraged to use it. It's pure SYCL, no extension. Using pin memory, it's important. It can tune your driver concurrency. Intel level 0 right now need a little more work, but it's already be done. If you just reproduce those results right now, you will see a really different thing. On AV and NVIDIA, SYCL, you have a better result due to this multiple pool, but you have a pull request already or some work done in Intel LLVM to be able to use this kind of pool of SYCL. Pool of stream, sorry. And also on AMD, using enable profiling have some side effect. So be careful when you profile. Sometimes profiling may destroy your concurrency. Thank you very much for this talk, and don't hesitate to send us any email if needed. Thank you.